Simple harmonic motion. Here are some terms we should know. Periodic, when a vibration or oscillation repeats itself back and forth over the same path. Equilibrium position, the position of a mass on a spring when the spring has a natural length and is exerting no force on the mass. Displacement, the distance x of the mass from the equilibrium point at any moment. Amplitude, the maximum displacement. Then there's simple harmonic motion, which is also called SHM, not SMH, which is oscillatory motion under a retarding force proportional to the amount of displacement from an equilibrium position. And systems that only have a force F acting upon them undergo simple harmonic motion, and they're called simple harmonic oscillators. Okay, so for simple harmonic motion, we need a frictionless world to demonstrate this, but we don't have that. So we're gonna do it anyways and pretend like it is. This is a spring, and this is a ball. And if you attach the ball to the spring, in a perfect frictionless world, you'd like pull the ball out, and then it'd go back all at the same speed and force and all that stuff. And simple harmonic motion is often described in terms of a ball attached to a horizontal spring lying on the table. When at rest, it's in equilibrium. When you move the ball so the spring stretches and then let it go, the ball keeps moving back and forth. Good. Okay, are you ready?
Mm-hmm.
Okay, so for our demo, we're going to be taking these two who are clearly different weights. They're on the same length string, and we're going to be pulling them back to the same level with this awesome Experience Princeton notebook that we have here. And how is stabilizing it for us, so that's good. Okay, they're on the same level, and when I let go, they should have the same period. Fingers crossed. We're taking a break.
Okay. Oh God. Damped harmonic motion. The amplitude for anything swinging slowly decreases with time until the oscillations stop altogether. This happens due to air resistance and friction. Energy turns to thermal energy out and is reflected in the decreased amplitude. When something is over-damped, the swing is so large that it takes a while to become equal. When something is under-damped, it takes several swings before coming to rest. Critical damping is when something quickly comes to equilibrium. For example, door closing mechanisms use shock absorbers to use critical damping, but eventually they go undamped with time as they start as, yeah.
Sick demo.
Sick demo. So, an example of damped harmonic motion. So, if I have this pendulum, if I have it swinging for a while, it'll eventually slow down and then stop altogether. So, yeah.
Are we just waiting for it? This is fun. Sick demo.
There you go. Damped harmonic motion.
Forced vibration.
Okay, forced vibrations. When an external force acts on a vibration, it's a forced vibration and has its own frequency. For example, pulling back and forth on something that's in motion. Wait, what else? Okay. Every structure has a resonant frequency. And for example, a swing. If you push a kid on a swing at a frequency that's equal to the swing's natural frequency, the swing will go high. But if you push at a random frequency or at random times, it'll just bounce around and won't do its job. In this example, Hawa is pushing me on the swing at a frequency equal to the natural frequency. Therefore, I start going higher.
Sick!
But in this example, I push Hawa at random times and at a random frequency. Therefore, she bounces around. Every structure has a resonant frequency, and when met with an external frequency that's the same, disaster can happen. For example, the Tacoma Narrows Bridge incident. The wind that day had the same external frequency as the bridge's natural frequency and caused it to twist and turn and eventually collapse.
But whatever the reason, Tacoma will rebuild, this time a bridge that will not provide a super thrill in the news.
Okay, there are two types of waves. The first are transversal waves, when a wave travels down a rope left to right and the particles of the rope vibrate up and down perpendicular to the motion of the wave. And then there are longitudinal waves, where the vibrations of the particles of the medium is along the same direction as the motion of the wave. Now it's time for a sick demo.
Okay, now go. Good. Here's some sick demos by, what grade are y'all in? Fourth graders. Keep going, boys.
You might want to get like this side. If this graph looks familiar to you, it should. And if it doesn't, well, you should probably go back to pre-calculus. This is a sinusoidal graph that a wave makes. Here we can see that the period and the amplitude are labeled. The period is the time required for one complete cycle to occur in the wave, and the amplitude is the maximum displacement of the wave.
One complete to and fro movement is, I don't know what it is. 1 second, let me talk to Sloth. Okay, ready?
Yeah.
Okay, so for our first sick demo, we're taking this and this on equal length strings. Sick demo. If you took a spring like this and attached a ball to it,
We are out of balls.
a ball to it. Can we get a ball? I'm gonna go get a ball.
Oh, I was gonna go get it.
Okay, you can. I'll say it. You can stop recording. Henry, what's wrong? It's cold. Very close. Okay.
And that's waves. Am I done?